We're now looking at interference and diffraction of light. When we talk about interference and diffraction, we really have to deal with light as a wave. Now, I realise in previous sections we've talked about light, and we've explained that light in some ways behaves as a particle, but also behaves as a wave. Now, some of Newton's ideas, when optics was first being laid down and all of the rules were being originated, were that the corpuscular theory was popular of light, which meant that light was very particulate in nature. It wasn't until someone like Christian Huygens and others like Thomas Young did a number of experiments to show that light really behaves like a wave. And if light behaves like a wave, then you can look at wave fronts or the path of light, as we've done when we've looked at such things as reflection and refraction, and you can describe the behavior of light in a wave-like sense. So, by tracing wavefronts and looking at the positions of various rays due to their propagation through different media, you can predict, say, interference between individual waves, and where you'll end up with, say, light and dark patterns for constructive and destructive interference, as we've discussed when we talked about the nature of waves themselves. Here's a quick cartoon of Christian Huygens, as opposed to my usual historically accurate diagram, which you'll see later. But for the purposes of diffraction and interference, we have to treat our light as a wave. Now, we've talked about refraction previously and how light changes as it passes from one medium to another. This series of diagrams shows how light is propagating from air into glass. When we look at something like this, we're dealing with the refraction of light that we've already discussed. There are basically three stages to this refraction. You have an interface here between air and glass. Here is a light wave coming in, represented by these three lines in terms of rays, and these vertical lines here, these green lines, show you the positions of various wave fronts, which essentially is, say, the actual wave that's propagating through. These lines, the white lines, are the path of the wave. Now, what will happen here is our light wave will come in with one velocity v1 and will interface with the glass here, which is also transparent. These wave fronts of light in the incident beam are separated by lambda 1. That's essentially a wavelength. So each wavefront is separated by one wavelength, lambda 1, in this medium. As they pass through lambda 2, then we have to look at a change in speed. We've said before that the denser medium, such as glass here, will have a lower speed of light than the air medium here, the more rarefied medium. As such, V2 inside the glass is lower than V1 outside the glass. This will give a corresponding change in the wavelength. This will change the positions of the wavefronts in terms of the refracted wave. So the light wave will propagate through medium 2 with velocity v2 at some angle compared to its original incident wavefront. And that means you'll see this change in the wavefront, and you'll see a change in the position of each respective wavefront. Now, we've discussed this before and said that the wavelength will change as the speed of the wave changes. That means our basic guiding formula that we've seen before will be F equals c over lambda, the speed of light over the actual wavelength of the light. Of course, this already takes into account the refractive index. The c over n over lambda n over n will end up cancelling the refractive index n. That means that v and lambda in any medium will change to lambda n equals lambda n over n, where this is the wavelength in a specific refractive index. So the equations that really govern these effects are things that we've seen before, and we've discussed these in detail when we talked about light itself, and indeed when we talked about wave mechanics. As such, light will come in, incident on the glass relative to some normal that we draw to the glass, and it will change angle. Theta 1 here in this medium, theta 2 here in this medium for the glass. N will be C over V, this being the refractive index. Frequently you see a discussion that will say that glass may be a denser or sometimes referred to as the more rigid medium than air. N1 sine theta 1, here N1 would be the refractive index of air, theta 1 would be this angle, and here we've got N2 and sine of theta 2. And finally, we can look at the velocity, wavelength, and refractive indices compared, where sine theta 2 over sine theta 1 is V2 over V1 is lambda 2 over lambda 1, which equals N1 over N2. And remember, these two should be reversed compared to these others. This is not an error. So, as we've just discussed, there will be a dependence of wavelength on the refractive index n. Light, of course, is composed of waves, and all those waves in the ray have the same wavelength and are in phase in air. We've discussed phase in terms of waves before, but if we are looking at a refractive index of 1, being that of a vacuum, or 1.00001 as it is for air, then all the waves in that particular medium will all have the same value of lambda, all have the same wavelength. That means there's no path difference here. When we talk about path difference, this will also bring about a difference in phase. So here we have monochromatic light, both of the same wavelength, impinging on two different refractive indices, N1 and N2. The ray that goes through N2 will exit with the same wavelength, but a different phase. So here, the wavelength of the light entering this medium N2 is the same as the wavelength of the light entering N1. As they leave, they will both have the same value of lambda, but will now have some different phase to them. And that phase difference between the two light waves will change as they travel through values of differing n. So you could imagine if we shine, say, a flashlight at a glass block. Some of the light will hit the glass block, and it will go through the glass block, and it will experience one particular value of n. The rest of the light misses the glass block and shines straight through air and will experience a different value of n. Both light waves will have the same wavelength of lambda, but both will have different refractive index values that they experience, so will have different phase. In order to find that phase difference, we have a particularly useful equation. What we really need to do is define how different two phases are of a wave, and this is usually referred to by the number of wavelengths. This is our phase difference, a delta n, and here that delta n is expressed as n2 minus n1. This is not the refractive index. The refractive index is little n over here. This is the number of wavelengths. Okay? So this is the number of wavelengths that are present. So n2 minus n1, or delta n, equals L, which is the path length, times n2 over lambda, minus L times n1 over lambda, which is equal to L over lambda, and then we can factor out our change in the refractive index, n2 minus n1. So this is how different, the capital N is how different the two waves are. What is their phase difference? How does the number of wavelengths passing through a particular point change? Delta n here, and that will equal L over lambda times n2 minus n1, delta refractive index, a different n. And what kind of value should you expect to see from n2 minus n1? Remember, these are going to give you some value that's in terms of the wavelength. So you'll see values from 0 to 1, essentially. A phase difference of 0.5 lambda, or 1/2 wavelengths, puts two waves exactly 180 degrees out of phase. We've discussed phase previously. If the waves are of equal amplitude and they're exactly out of phase, then you'll see them undergo fully destructive interference. That means you'll end up with a dark fringe. A phase difference of 0 or a phase difference of 1 basically being the same thing, so 0 times lambda or 1 times lambda, will represent a constructive interference and give you a bright fringe, a bright line when projected onto a screen. So we can conduct the experiment we discussed previously and shine light through a medium and then look at the pattern on the other side of that medium. All the light that's half lambda out of phase will be dark. All the light that's 0 or 1 lambda will give us a constructive interference and give us a bright fringe. So one phase difference is either 2 pi radians or 360 degrees. I tend to favour using radians where possible, but books are often interchangeable depending on the situation. So be careful when you are expressing radians or degrees as to the context of the question, but I will try to stay in radians where possible. And there's the interference pattern we would get. If we're looking at them being either 0 or 1 lambda, then we will see these bright patterns here, these bright bars, these bright, what are referred to as fringes. And if we're looking at things being out of 1/2 lambda, 1/2 wavelength, out of phase with one another, one wave to the next, then we will see these dark bands. And that is what will give us an interference pattern. As we pass our light through a medium, we can project this pattern onto a screen and we can see these light and dark bands as the light interferes with itself, as the different waves basically propagating through the medium interfere with one another. And remember, this is for light of the same wavelength initially, changing as it passes through a medium and undergoing a phase change. And what actually gives rise to this phase change? It's not just some spontaneous, as if by magic, phase change here that occurs because of the material. It's actually due to a difference in the path length. You can kind of look at this situation here as a car skidding around a corner. One tyre on the very outside of the corner will travel a different distance to the tyre on the inside corner. And you'd also see a very similar effect by slipping your foot sideways as you round a corner. That means that this wave here that's travelling through this medium travels a slightly different distance to this wavefront that's travelling through the medium over here at A. So these two wavefronts are actually undergoing a slightly different path. So these path changes, or the change in path length, result in a change in phase between one wave and the next. One has travelled slightly further distance than the other, which means it's lagging slightly behind, and its wavelength is no longer in phase with the other wave. So we can express this in terms of wavefronts. So the phase difference between our two light rays can change if the light travels through paths with different length. The light then has to reconverge on the other side, and that will give us light that's slightly out of phase and give us our interference pattern. Now, the phase difference can actually be calculated. And if we're looking at the calculation for the phase difference, we're looking at our light traveling through two different paths. For fully constructive interference, we can look at the path length divided by the wavelength. So for fully constructive interference here, delta L, the change in the path length divided by lambda will be values of 0, 1, 2, any integer value. For fully destructive interference, our value of delta L over lambda will give us 0.5, 1.5, 2.5, any half value. As we said, being completely out of phase is to be out of phase by 0.5 of a wavelength, 1/2 wavelength. So any value of 1/2 wavelength will give us destructive interference. This formula gives you the position of your constructive interference, your bright bands, and this predicts the position of the destructive interference. So, let's take a look at using these. I've just hit you with several formulae, and we should really take a look at these. Here we have two light waves, both of wavelength 550 nanometers. They then enter two media, media 1 and media 2. The light waves are equal amplitude and in phase when they enter N1 and N2. Medium 1 here, this blue medium, is air. Medium 2, N2, is transparent plastic of N equals 1.6. We also have a thickness here of 2.6 microns, or 2.6 times 10 to the minus 6 meters. The question then states, what is the phase difference of the emerging waves in wavelengths, radians, and degrees? So here we're doing it all. So remember, our formula for delta N here was N2 minus N1 equals L over lambda, the wavelength, times N2 minus N1. Well, the path length here was 2 microns, or 2.6 microns. So this is 2.6 times 10 to the minus 6 meters. This is how much the thickness of the actual plastic film the light wave went through. And here we've got lambda, which was our 55, essentially 550 nanometers, or 5.5 times 10 to the minus 7 meters. I would probably just put times 10 to the negative 9 on the end of my 550. N here is the difference in refractive index, 1.6 for the plastic and 1 for the air, giving us a value of 2.84. So our phase difference here, N2 minus N1, is 2.84. So what does that actually mean? Well, the phase difference of our emerging waves is now 2.84 times lambda, the wavelength. Now remember, one wavelength is equivalent to 2 pi, or 360 degrees, one complete cycle of the wave. So our phase difference here, if we convert it, 2.84 lambda, will be 17.8 radians, or 1020 degrees. So 2.84 times 360, or 2.84 times 2 pi. So phase difference here can be expressed in three different ways: in radians, in degrees, or in terms of N2 minus N1 delta N. So the answer, 2.84, 17.8, or 1020, are all equally valid, depending on the context of your question. So the effective wavelength difference, if we decide to express it in terms of wavelengths here, will be 0.84 wavelengths. So this is 2.84 essentially, but this is two whole wavelengths. So every one value of 1, your light is in phase. So at 1, the light is in phase. At 2, the light is in phase. So effectively, this is what this really means, the effective phase difference is that the light rays are only 0.84 wavelengths apart. So even though the light underwent a phase difference of 2.84, it's only 0.84 away from its essentially brother or sister or whatever you want to call it, wavelength that went through the uninterrupted medium of air. So just to summarize, delta n will be L over lambda times the change in the refractive index. Don't mix up your n's. This L value is whatever the path length was. How far through the medium did the light travel? In our case, this was 2.6 times 10 to the minus 6, 2.6 microns, and this was 550 nanometers in terms of the wavelength. N was 1.6 and 1 to give us 2.84, which gave us, in the end, our phase differences of 17.8 radians, or 1020 degrees, giving us our effective phase difference of 0.84 wavelengths. Please make sure you understand the difference between the total phase difference here of 2.84 and the effective phase difference of 0.84. 2.84 here is because we changed the wavelength by 1 and then by 1 again, putting the waves essentially in phase, out of phase, and then back in phase again. And then finally, out of phase by a value of about 0.84 lambda. So this is the ratio of the wavelengths, one to the other, and this is the actual value in terms of radians or degrees, in terms of the point they are reaching in their cycle. So that was our discussion of interference and how we take account of interference in the case of, say, the interference through a slit or through two different media. What we want to look at now is the effect of diffraction. Now, diffraction occurs not because we're traveling through different media, N1 or N2, but because waves bend as they move around an object. Now imagine looking at, say, a rock in a stream or an island in the ocean. You do not end up with a big dead spot of dry land right behind an island or right behind a rock in a stream. What you end up with is the waves bending around that particular object and continuing to circulate behind them. Think of a boat moving through the water. As a ship or a boat moves through the water, waves move past it and around its shape and then still encompass the space behind it. You don't end up with a large hole behind an object. Now, as water waves essentially bend around an object, that means they diffract around it. And you actually have this very same effect when you're dealing with light. Light will bend around an object and will move behind it. I realize you do have shadows, and the intensity of those shadows depends on the light and the direction and how diffuse that light is. But light does bend around objects or corners a little bit. So when we talk about diffraction, let's continue our water analogy. If we take a look at this case, here is, say, two bars creating an obstruction in a water tank. We can then create waves which will travel as large, long, straight waves in a straight line through our water medium. They will then hit this obstruction. This will bar the passing of all of this part of the wave. The wavelength, as you can see, is the same here before and after this particular interaction. If we go straight line through the obstruction here. So here our wave comes in, hits this obstruction. Only part of the wave is now allowed through, as the rest has been blocked by this bar. This wave moves through, and as you can see, it now continues to propagate the other side of the obstruction. However, on the other side of the obstruction, it's now no longer one long line here, as this particular disruption in the medium was, but now it's circular. The waves are curling around the object, around the sides of this particular slit. So, water waves will encounter this kind of obstruction, and then they will spread out as they pass through a slit in the obstruction. And this is the effect of diffraction, and it's heavily dependent on what is the relative wavelength of the particular object compared to the size of the obstacle itself. And here we have the same obstruction, this block sitting in this series of waves, in two cases. As you can see here, we actually have a case where here the wavelength of the wave is a lot smaller than the object. Here we have a wavelength which is much larger than the object. The effect of diffraction is far more pronounced if we look at a wavelength which is much larger than the object than if we look at an object that's much smaller than the object. So in this case, it's less. It occurs less if the wavelength is smaller than the object, and occurs more if the wavelength is larger than the object. And where could you actually experience this? Well, back in the days of early radio, there were entire valleys and people who lived in, say, the mountains of places like West Virginia who couldn't receive long-distance radio transmissions. They would have to wait until signals were being bounced off of the ionosphere and bounced off of the atmosphere to actually to actually pick up radio signals in some places. And this is why you end up with places like the Green Bank Telescope, which are built in valleys in the middle of nowhere. So if you look at radio waves, AM radio waves have longer wavelengths than FM radio waves. Those long wavelengths actually end up diffracting around large buildings and mountains, which FM transmissions could not do. This is less of a problem now people have moved to digital transmissions, but still very large masses such as mountains will block radio transmissions. And what we actually mean by diffraction here is, as you can see, over here we have a transmitter. That transmitter is putting out AM radio waves. As the radio waves encounter a very large hill, they will be absorbed by that hill. Radio waves are very long wavelength, and AM, amplitude modulation, much more so than frequency modulation. Consequently, as they hit the hill here, we end up with diffraction occurring, and that means if you're on this side of the hill, you can now pick up these transmissions. If you were looking at an FM transmitter, it would not diffract nearly as much, and if you're on this side of the hill, you would not receive any particular transmission. You will still see shadows if you were, say, behind this tall building, or right here under the lee of this hill. So if you're very close to the hill, you might not pick up this transmission, but further away over here, or further up the hill over here, you may pick up this transmission as it diffracts around the edge of the hill. So recall when we talked about interference. When we overlap two waves, we can form a new wave, the principle of superposition. So in this particular case, we took a mechanical wave, one person flicks a rope this way and propagates a wave from left to right, another propagates a wave from right to left. As those two waves interact, they add to one another, they superpose, and you end up with a larger amplitude. Those waves then continue on their happy way, this one going to the left, this to the right, they then subtract, and the superposition interaction ends, and the wave continues on uninterrupted in this direction and uninterrupted in this direction. Now this is exactly what we can do when we look at radio or any other electromagnetic wave, such as visible light. So if we take two or more light, or sound, or mechanical, or light is an electromagnetic wave, of course, electromagnetic waves of the same frequency, we can superpose them, we can combine them. That means, as we saw in the previous case when we talked about interference patterns, they will reinforce or cancel one another. That means when you see a bright fringe that we discussed previously, what we're really seeing is a reinforcement of the wave, a superposition, an increase in the amplitude of the resulting wave giving a bright fringe, or a decrease in the amplitude of the resulting wave giving a dark fringe. So the amplitude of the resulting waves is equal to the sum of the amplitudes of the combined waves, something we've discussed a little more before. And it was people like Christian Huygens who did a lot of experiments in this. As I said before, Newton's prevailing idea of light was the corpuscular or particulate theory, where light would behave very much as a particle. He wasn't far wrong, but for all of the wrong reasons. It wasn't until the quantum revolution or the introduction of modern physics during the late 1800s and early 1900s that we confirmed that light does indeed behave as a particle. But for the purposes of what we're looking at right here, we're really dealing with interference due to waves. And this is what Huygens put together. The wave model explained diffraction perfectly, and if he looks at wavelets expanding in every direction, we can look at them being in step or in phase, or out of step or out of phase. And it was really Thomas Young that came along and put this completely together and proposed this wave theory. Thomas Young is another one of these people who just about did everything. In fact, there's a whole book published called The Last Man Who Ever Knew Everything. And he really was one of these geniuses. And he did work in just about every field of engineering, mathematics, and physics. And he determined that optics could be explained if light were a wave with a really small wavelength. So he took the work of Huygens here, that was done in the 1600s, and really ran with it, and really put to bed this idea of light being a wave and not a particle. We know they're both, but the actual particulate nature does not affect it in the way we're talking here. So Thomas Young read through Newton's optics and determined that optics could be explained by these really small wavelengths. And that's where the Young's double slit experiment comes in, an experiment you might see in an average physics lab. And what this is a measure of light. He proved that the wave nature of light, and he did so by directing a beam of two really narrow light rays from closely spaced slits through a barrier, like we've seen before, and that light diffracted and overlapped the two rays. So this gave us the interference pattern that we've seen and created those light and dark bands. And here's what's actually happening. Here's our wave fronts coming in, essentially parallel to one another. They're hitting our obstruction, as we saw with the water waves. The waves are then passing through these two slits. As they do so, they will propagate outwards. They will diffract either side of those slits. And, as you can see, they will actually interact with one another. That means you can see parts of this wave are being added together, while other parts are being subtracted from one another. And you can actually see where these light rays actually cross over one another. And as you could probably imagine, by changing the wavelength, we can change the actual spacing between our slits, between our bright and dark fringes. We will get constructive and we will get constructive interference from these interactions, which will give us that bright, dark pattern. So a small part of the light passes through the single slit, essentially allowing one wavelength to pass. This is how he proved that it was a very small wavelength, by having a very, very, very fine slit. The waves are in phase, and their crests and troughs will reach the same point at the same time. The waves spread out after they pass through the slit and fall on that double slit, and then they diffract and they act as two sources. And those circular waves spread out from the barrier, and they add or they subtract. Where two crests overlap, you get your constructive interference, and the light intensity gives you a bright band on the screen. Where the crests and troughs overlap destructively, they give you a dark or part of your interference pattern. So here essentially is the experiment. We just saw the effect. Here he took monochromatic light, essentially a white light source, shone it through a single slit here to get a slight diffraction, and then we have two slits, S1 and S2 as they're usually called. The light hits these two slits and then diffracts as it goes through. This second diffraction through these two slits causes those wavefronts to interfere with one another, as we saw in the previous diagram, giving you a bright and a dark and a bright and a dark and a bright and a dark fringe, with one very bright central fringe. Your interference pattern can be projected, and you can predict the wave nature of light. And there's essentially what's going on in one simple diagram. Here's our light source, goes through our first slit, giving us this circular wave like this. This then impinges on S1 and S2. This causes further diffraction, which, as you can see, gives us our constructive or destructive interference. Here the white waves are added together where they intersect, and they're subtracted where they are out of phase, giving us a minimum. If we look at our viewing screen, our maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum. What's next? You guessed it, a maximum. So this is the interference pattern we will see, and here's the actual interaction of those waves. So you can see where these waves are added together, where they're coincident, and where they're not added together, where our minima are, and where they're out of phase, giving us our dark fringes in our pattern. And there's the interference pattern that we saw previously projected onto a screen, with our subsequent bright and dark fringes. Note that they're not all the same intensity. The central line here is generally a very bright line, whereas the subsequent lines tend to get less and less intense as you go further out. As you can see, there's a large pattern here of dark regions here, where we're looking at destructive interference here and here in a large band, and then we're seeing more constructive interference further out. So when we look at our constructive interference, we're looking at an increased amplitude of our wave. So our waves are coming in, they're interacting and giving us a larger, increased amplitude light wave, which is brighter. Our destructive case, we're looking at the light waves being opposite, essentially in phase, adding together, and we're looking at a minima, essentially a maxima, giving us an overall reduction in our amplitude, which we will perceive as a reduction in the brightness of our line. So in phase, if we add this wave, the green wave, to the yellow wave, we'll get a higher amplitude wave. If we add two waves that are lambda over 2, or 0.5 lambda as we saw, out of phase together, then we will end up with a complete cancellation. Half wavelength out of phase will give us one of our minima. Here's a maxima, here's a minima. Once they're one full wavelength out of phase with one another, the effective wavelength is essentially negated. So effectively, these are back in phase with one another. Even though one wave is essentially full 360 degrees out of phase with the other one, it's back in phase and will add together, and it'll give you your bright fringe. So bright central fringe, dark fringe, bright fringe. It's not that the light is unaffected when we're looking at, say, secondary or tertiary bright fringes, or indeed the case when we're looking at dark fringes. It is affected, it is out of phase, but it's exactly one wavelength or more out of phase. So for our constructive case, here we're looking at our waves overlapping and giving us our new amplitude. Our destructive case, where we're out of phase by either 180 degrees, pi radians, or lambda over 2, we're essentially looking at these being completely out of phase, which gives us 0, gives us our destructive line, and then for anything else which is partially in phase, we'll see a slightly darker line. So you can see any particular combination of these. This would be perfectly in phase, a very bright line. This will give us a very dark fringe, give us our minima where it's completely black. And here, where we're partially in phase, we'll see a dim fringe. So where could you actually see this effect? Well, a place you can see this effect is down in my lab here, where we actually take photos of these things all the time. And here is an actual soap film that's being run and actually being imaged here. And as you can see, there are bright and dark lines in this. This is not to do with, say, the flow pattern of this particular film. This is to do with the interference pattern that's set up in this film as light passes through it. Think about looking at oil. If you're looking at, say, a particularly old car that's leaking oil everywhere, you can see this in the road a lot. If there's oil in water, you can actually see a lot of different colours in that. It's not that oil is many different colours, it's just that the oil is sitting on the surface of the water and you're seeing reflection and phase differences giving you an interference pattern. So the interference of light from soap bubbles, you can even see this in soap of course, or oil and water, is what gives you those different colours. And that's what gives this pretty banding pattern that you see in this soap film or this oil. So why do we see a phase difference when we look at thin films? Well, light, or selected light rays, can travel different distances in the medium. There's different thicknesses of soap film or different thicknesses of oil film sitting on your water. Rays go through different material with different refractive indices. That means the reflection from a medium with a bigger index of refraction is different to the reflection from a material with a lower index of refraction. This means that you see path differences from your light, which gives you the different colours, essentially an interference pattern from these different films that reaches your eye. So if we take this particularly creepy diagram with a disembodied eye, here we have air that you would be standing in looking at this scenario, we have a layer of oil, and then we have a layer of water. Light essentially comes in, interacts with the system by passing through the layer of oil, hitting the water below, and then being reflected off and coming to your eye. Light is reflected from the upper surfaces and the lower surfaces, so the water beneath the oil and the oil itself. This means that you're receiving light essentially when looking at, say, something like a soap film, reflected from the front of the film and the back of the film. This means that the path length is different for different rays of light, and as such you will experience an interference pattern like this. So from thin films you can see constructive interference, and they'll give you the typical central band with further bands on either side. The dark areas again being destructive. White light, essentially in a double slit diffraction, will give you the same effect as looking at these different films. So the incident light is reflected at A here from the top surface, from the oil, and then the transmitted light goes through and then reflects off of B. So our initial reflection occurs from A, our second reflection occurs as the light passes through medium A, through the oil, and bounces off medium B, which is the water. This means the light reflected at the lower surface travels further than the light at the top. So the light from the oil here comes down, bounces off, and comes to your eye. The second pathway, the light passes through the oil, hits the water beneath, and then bounces off and comes to your eye. So there's two path differences, changing the wavelength, changing the phase essentially. So the wavelength is the same, I should say, but the phase is different from the light hitting the air and the light hitting the water. So if path difference ABC is equal to one whole number of wavelengths in the film, then you'll end up with constructive interference, and part will be bright if the film looks bright. If we're looking at a different path difference, ABC, then you'll see a different interference, maybe 0.5 lambda, 1 lambda, 0.85 lambda, 0.75, and especially if the film is flowing, you'll see different thicknesses, and that means different paths are taken, different distances, and so different phases. And the colours that you'll see in soap and the colours that you'll see in oil. So if ABC equals exactly 1/2 lambda, 3/2 lambda, the two waves will be exactly out of phase. And in that destructive interference case, an area of the film will look dark and show no reflection. That means it'll look transparent to the material below, and you'll be seeing, in the case of the oil and water, all the way through to the water. And those variations in film thickness will change the path difference and affect the colour of light that you're going to see.
So if we look at interference in soap films, we're really talking about an effect of reflection from the front and back of the film. Here we have a soap film, index of refraction of N of about 1.3. This is usually about the same as that of water. Here we have air gaps of 1 and of course 1 respectively. If we look at the paths of the light rays coming to this huge disembodied eye once again, what we're really seeing here is a light portion of the light ray bouncing off of the top surface and more of the light ray transmitting through the film and then bouncing off of the back surface, both of which will come back to the eye. At this point we're seeing two different path lengths. We're seeing essentially this length as the ray bounces off the top surface, and then the same length plus L essentially for ray 2. That will produce a phase change upon reflection. That phase change will either be a 180-degree phase change when reflecting from the soap film, or no phase change at all, given that it could be 360. So if we look at the path differences here, essentially we're looking at the path difference being L, the film thickness. So we can say that 2L here is going to be 1/2 lambda n. Why is it 2L, I ask? I hear you ask, Dr. Horn, you ingenious polymath? Because we're looking at the light ray travelling through the soap film and then coming back through. So it has to go through, bounce off of the back surface, giving us L, and then another L, so giving us 2L. So the path length difference here is 2L, which is equal to 1/2 lambda, 1/2 wavelength. So the formula for the interference pattern from this soap film reflection will be 2L is equal to M, which is the order of the interference. Is it the first fringe, second fringe, third fringe, blah blah blah, in integer values, plus 1/2 times lambda, the wavelength. Well, lambda n is n over 2. Add 1/2 lambda, and that accounts for the 180-degree phase change, giving us constructive interference. So, if we want to predict the positions, the order of our constructive interference, m, we can do so through this formula. Now, likewise, if now the huge disembodied observer's eye is the other side of the system, so here now light is transmitting through the soap film, we'll still see the same effect. The reason we'll see the same effect is light can travel straight through, transmit straight through, or it can bounce off of this interior part of the film, back up, off the top of the film once again, and then back to the eye. So again, we'll see a 2L path difference between light ray 1 and light ray 2. So for constructive interference, we have to look at our integral values again. So we can look at 2L being m lambda over n, or the corresponding wavelength of 2nL over m, where m is some integer value for the order and n would be 1.35. So let's take a look at a problem here. Here we've got a soap bubble which appears green, which means it has a lambda, a wavelength of about 540 nanometers. And that's from a point at its front surface nearest the viewer. So here we're looking at rays bouncing off of the front surface of the bubble. What's the minimum thickness of the soap bubble here, if we're looking at this kind of value, if the whole bubble appears a greenish colour? And we've got an n of 1.35. Remember, light rays will reflect at 90 degrees. The inner surface of the soap bubble film also reflects. So the path difference of two reflected rays is twice the thickness. In our previous example, L was the path. Here it's just T. It's given as thickness instead of L. So T is the film thickness. The light reflected from the outer surface undergoes a 180 degree phase change, so the N of the soap is greater than the N of the air. No phase change occurs due to the reflection from the inner surface. For the thickness for an interference maximum, we can use lambda of light in the soap. So a 180 degree phase change at only one surface is essentially equivalent to half a path difference, half a wavelength path difference. So the green light is bright when the minimum path difference is 1/2 n. So we can talk about path difference in terms of thickness L, or we can talk about it in terms of the fraction of a wavelength that it's changed by, the phase change. So we're expressing a thickness essentially as a phase change. So twice the thickness here is lambda n over 2. This means the thickness is the wavelength inside the film, lambda n, over 4. That's 2t's lambda over 2. This gives us lambda over 4n. Substituting in now, we can say 540 nanometers over 4 times 1.35 will give us a thickness of 100 nanometers. This result essentially could be used straight out. Here we're looking at a simplification of that.